All right, hey everyone, I'm Pat Viafor, and I'm here to talk to you about typing. No, not this sort of typing, not typing on a keyboard, we're talking about Python typing. So I say Python typing, and let's talk about C++ first. Who here works in C, C++, Java, one of those, or used those in the past? You see code like this, it looks very familiar. There's types here, unsigned int, a vector, unsigned int. Those are types in the C++ system. If I were to take a look at Python code, I look like this, way simpler, x equals 10, v equals, a list of it with x in it. A lot of people look at this and say, wait, does Python have types? I don't have to type all these things here. Yes, Python does have types. They're just not front and center within the language as you type them. We have something called dynamic typing. So C++, C, Java, they have something called static typing. The types are needed by the compiler to infer some meaning. In Python and other dynamically typed languages, those types are done at runtime. So runtime information is passed along with your objects, and the objects know their own type. So I can see this in Python, where if I do type of 10, I get int. This is a type int. Type of ABC, that's a string. Even functions are types. So I can say, what's the type of print? Well, that's a built-in function or method. Even types have types. So I can say type of int, and that is type. And actually, if you do type of type, it's type, and recursively it stays being type. So Python does have types. We just don't see them that often. What is a type? I want to kind of level set here. What do you guys think a type is? If you were to describe it to me. Oh, audience participation.
Version of API.
API, that's a good point. Classifications. I'll say a type is a semantic representation of data. Here's some data. Somehow we have to know what that means. A type provides meaning to that data. So there's kind of two things here. How data is represented in memory. I'm not going to talk about this in that talk. That's a great talk if you're getting into CPython or the Python internals. Instead, I'm going to talk about what options are possible on it. To me, this is what the big benefit of a type is. What operations are possible on that type? I can't talk about typing in Python without mentioning duck typing. Who here is familiar with duck typing? A few hands. So duck typing is called, if it looks like a duck and it quacks like a duck, it's probably a duck. And every time you hear that for the first, if you've heard that for the first time, you're like, that doesn't tell me anything. So let's dig into that. I have a function here called print and clear. It takes a collection, I print it, and then I clear it. What duck typing says is as long as I adhere to a certain interface, in this case can be printed and can be cleared, well, then I can be used in this function. So I can be a dictionary, I can be a list, I can be a set. It doesn't really matter. This is that dynamic typing. I don't have to specify my type up front. As long as my type adheres to this interface, I can pass it in and it will just work. I can even create my own types. As long as they can be printed and cleared, I can pass them to print and clear. That's what duck typing is. Duck typing is simply just, I fit to an API, I fit to an interface. I don't really have to tell my functions about those types up front. I also want to talk about primitive versus composite types. So primitive types are your bare bones, most atomic types that you have. And here are what's considered the primitives of Python. You have int for your integer types, floats for floating points, boolean, true, false, string, a grouping of text, my none type, which is what the type of none is. And then you have composite types. These are types built up of primitives and other composite types. So if you have to stack all these little types onto each other as this part of a big Lego behemoth, well, that's a composite type. And Python has some built-in ones, bytes, complex numbers, name tuple, modules, etc. All of those are composite types. They're types built up of primitives and other composite types. You also have collections in Python's type system. So there's a list. If I wanted a list of information, 1, 2, 3. Next one is a tuple. That's an immutable list, if you want to think of it that way. A list that can't be modified. So that's useful. There's a set. So that's a list of information that has no duplicate information. If I were to add a 1 into this set, it actually wouldn't show up twice. It would still just be 1, 2, 3, because I can't have duplicates. And dictionaries. where I can map one value to another. It's almost like an association. So the string 1 maps to numeric 1, string 2 maps to numeric 2, and that can be arbitrary. I couldn't mix those up where string 3 maps to 1, but I wanted to be sane for this talk. So why do we have types? I've told you what a type is. Why do we even have them? Why are they important? Well, again, I have 2 reasons for this. One is to communicate intent to other developers, and 2, tooling can use types to help you catch mistakes. I think that's very important. These 4 collection types convey intent. I have a list of information. Should it be immutable? Should I not be able to change it? Well, if so, I should use a tuple. Should I not have duplicates? If so, I should use a set. So if I see these in code, they convey types to me as a developer. Even though I'm not talking face-to-face to whoever wrote them, they passed a little message to me from the past, and they time-traveled. And future me is like, oh, I understand why you did this. If I see a tuple, I know I shouldn't be modifying it. Likewise, if I see a list and I see a comment above it that says, should not be modified, that tells me, like, well, why didn't you use a tuple? We use types to help convey intent to future programmers. A quick note on intent. Let's say I throw this number up here. What does this number mean? Madison zip code, or maybe it's the number of people I wish were at this talk. And depending on what my intent was, it dictates what type this is. What type should this be?
Int.
Int? So a type is what behaviors are defined on it. Do we often add numbers to a zip code?
No.
Do we normally subtract or multiply zip codes? All things we do on ints, right? Zip code probably should be a string because we don't do numeric operations on it. We do string operations. We might append that 4-digit code at the end. We might append it to another address. If you just see this in code, you might be confused. Is it an int? Is it a string? If we can convey what sort of type it is, that will help people in the future understand what behaviors are possible on it. You can create user-defined types. Here's an enum. This was introduced Python 3.4, I think. I don't remember exactly. But the enum lets you say, just like you would in C, C++, Java, C#, just a collection of different values. So red is 0, yellow is 1, green is 2. I have a traffic light. And I can do things like, hey, if a light is equal to red, do something. Or I can say, hey, give me a traffic light where the number is 2, and that gets me green. That's really nice. I can now start using that in my type system, and it catches errors as well. I can't add numbers. What's red plus 1? Well, if that were just a 0, people are like, oh, of course, that's 1. But that's a weird thing to do when you're talking about discrete values like red, yellow, green of a traffic light. Additionally, if I go out of bounds and say 4, I get an error. That's really nice because I want errors. I don't want undefined behavior going through my code because I didn't understand that I have unrepresentable states in my system. I want to be able to restrict what I can represent. Those are enums. We also have data classes and introduced in, homework. Forgot I had a homework slide. I'm not going to have time to cover everything that I want to. If you want to look more about enums, there's int enums, which do offer a little bit better integer conversion. There's int flags for things like if anyone's familiar with like bit flags, something very similar. Unique helps you out making sure that your enumeration values are unique. And auto for if you want to make sure that you don't really care what those values are. I used 0, 1, 2 as part of my enum definition. I could have said auto and just said I don't really care what these numbers are. Please don't ever make them numbers. We also have data classes in terms of a user-defined type. So this is a data class. Data classes were introduced in Python 3.7. I have a presenter, and I have some fields in there. A name, which is a string, age is an int, and toss, which is a list of strings. I'm going to talk more about the things to the right of those colons in a little bit. If you're not used to that syntax, don't be alarmed. But when defining data classes, you do define what types these are. And that's really useful for when people want to see, well, what does this type mean? If I gave you talks and you didn't have any type information associated with that, you'd probably think it's some sort of collection. But is it of strings? Is it of a talk object that's 40 files down the road in your file system? Don't know unless I have that type annotation there. With a data class, I can easily create instantiation of it. I don't need to write any sort of init method, for those of you familiar with classes. And I can just access attributes right in there. So p.age prints 32. That's nice. I like data classes more than named tuple. If you're a big fan of named tuples, I highly encourage you to start looking at data classes. They do a lot of the same things that named tuple does. I like the API a little bit more. That's an opinion, though. You can argue with me later if you want, if you think named tuples are better. The data classes also, some more homework for you. Data classes also have some fields called frozen, ordered, init var. Whether you want to, so frozen's whether you want to make a data class immutable or not. Ordered, if you want to provide ordering attributes on a data class, so you can do less than or greater than. And init var is a little bit of a special case. I encourage you to read about it for when you want to have variables in your class just used for initialization, but not necessarily defined as a type. So go look those up if you're interested in more data classes. The last user-defined type I want to talk about is classes. So this is a class. I have a presenter. I have an init method. This is a constructor. This is what happens when I create an instance of this class. I say, well, I'm going to give myself a name, and I want a counter of talks. So self-talk counter, what's counter? And I have a function that can operate on this class. This is a behavior on my type called giveTalk. So given a talk, I'm just going to increment my counter. So as I give talks, my counter goes up based on talk. So if I give this talk 3 times, I'd end up with a counter that says, this talk's been given 3 times, all the other talks have been given however many times I've given those talks. What makes a class special is an invariant. Who here has heard about invariants before? You people. An invariant is something that should always be true about your type. It allows you to reason about your type. So in this previous example, presenter, my invariant is I can't ungive a talk. Once I give talk, it may only be incremented. If I were doing this with a raw dictionary or a list, people who are using that type can just say, well, I can add and subtract numbers to this counter all day long. By restricting the interface of what I can do here in my presenter class, I've created an invariant, something that is true through the lifetime of that class. It might be that a list must always be sorted. It might be, I was talking about classes in the last office hours, and we were talking about pizza. It might be, hey, your toppings always go on top of the cheese. Now, some people might argue on that, but for the class we were designing, we said, hey, an invariant is toppings go on top of the cheese. They're called toppings for a reason. And by creating classes, we were able to create an invariant that's restricting the operations and behaviors that can happen on that class to be able to reason about that type. And that's really important. So when you have an enum, you're talking about a selection from discrete values. When you're talking about a data class, you're saying I'm bundling some related fields together. And when I have a class, I'm saying I'm bundling some related fields together, and there's some invariant tied along with that class. Notice I did not put dictionaries up here. Dictionaries, a lot of people use dictionaries as a type, but the problem is a dictionary really doesn't convey any sort of meaning to future developers of these are the behaviors you should be doing on this dictionary. These sort of types help you out with that. So earlier I asked why we have types, and I've been mostly talking about communicating intent to other developers. I'm now going to talk about the second piece, how tooling can use types to help you catch mistakes. So if I had that presenter class and I said I wanted to do something with that presenter class, I never had a function called do something. I only had a function called giveTalk. So I write that in my Python interpreter, and it says attribute error. My type object presenter has no attribute do something. And this is duck typing at play again, because there's nothing that Python can really do to catch this early, except for right when I invoke it, go do a check at runtime. Is there a method do something on presenter? It doesn't know until it goes and tries to execute that. And so how can we have tooling catch that for us? So Python 3 has introduced type hinting. A lot of dynamic languages have been moving to type hinting. 2 of my other favorites, Clojure and Elixir, certainly have, and Python's no exception. This is type hinting. You saw it a little bit in data classes. It's when you define a variable, you put a colon and then the type that you want to the right of it. So x int is 0, y is a string, it's set to ABC, p is a presenter, and I'm making a call to make presenter. Do I actually do this a whole lot? Sometimes. Most of the time, this can be auto-infer, like x int equals 0. Of course it's an int. It's 0. What else would it be? I don't annotate my variables all too often unless something complains at me. Instead, I annotate my functions a lot more. So when you create a function, you can also annotate your parameters and your return value. So in this case, I have a getPrice function. Doesn't matter what it does. I have some base price, which is a float, tax, which is a float, and a state, which is an enum of all the states in the United States. so that I can go calculate a float, which is my final price. So if I take a look at this as a developer, even if I didn't write this, I can have an idea, here's how I use this, here's what I'm getting out. It's a piece of information that's embedded within the language itself. I don't have to rely on doc strings or comments, which may go out of date. We've all seen outdated, bad comments. I don't have to rely on those. I can have those right in my language. And there's something nice about here, autocomplete. So I have a class called presenter, I have my init, my give talk, and I have a function called get list of talks here. I create a presenter pat, I give 2 talks, and I'm going to create a function that will print out a list of all my talks. So it's going to take a presenter. I am not going to do type hinting at this time. I'm just doing a new line separated list. If I type presenter dot, I don't get any sort of like type complete or autocomplete on here whatsoever. I can write get list of talks, okay, but if I'm like thousands of lines away from the definition, it's kind of annoying. Let's try that again, but with type hinting in here. I'm going to type hint, I'm going to say, hey, this is a presenter. And now, when I do that print, I'm going to do my new line separated list of talks. I'm going to do presenter dot, and look, I have autocomplete. If that's not a reason enough to do type hinting, I don't know what is. I mean, look at that, it's so beautiful. I get a list of all the things I have. Like, those of you who use IPython or Jupyter Notebook, like you have tab complete for like built-in functions, but the problem is in functions you write on your own, if it has no idea what type that is, type hinting can save you on that. It's really nice. However, it's not enough. So those of you who are familiar with the DevOps mantra, shift failures to the left, what that means is if I catch an error at runtime, I have to ask myself, how can I catch that earlier? Because runtime errors are expensive. Customers might experience interruptions. I might get incorrect results. How do I catch those earlier? Python doesn't really have a compile step that people interact with a whole lot. So how do I catch that? Well, mypy is the answer. MyPy is a static analysis tool, which means it looks at your code. It does not run your code, but it introspects the actual text of the source code and tries to find problems with it, specifically with types. So if I were to write this code in Python and run it against MyPy, I would get, hey, I can't assign a string to an int. That's an error. I can't assign an int to a presenter. That's an error. I want to find those values really early. I have some
runtime error though?
It would give you, so these 2 lines would not give you a runtime error. Because of dynamic typing, it doesn't matter what you set to it. MyPy is a check time. I'll get into that a little bit later.
So the wrong int doesn't force that to be an int at runtime?
It does not force it to be an int at runtime, no. And that's why it's type hinting and not strict typing all the way through. It's hints to the checker that this is the type what it should be. We'll get into that a little later. So I have a function, +1, takes an int, returns an int, adds a number +1. Let's imagine there are thousands of lines of Python between that function and where I'm actually using it. I have some value x equals 0, and I print out a number. If I were to change x to ABC, MyPy would catch that, because it says, hey, I can't call +1. Actually, I'm sorry, I have a typo. That +1 should be an x. My apologies. Imagine that that's +1 of x. What you might not have realized is if that were to be +1 of x, this is actually a type error already. Anyone caught it? Pythasis in here? I am adding a string and an int, and here's the MyPy of it. So forget the x equals 0. Apparently that was a red herring that I didn't even intend. If I'm trying to append a string and a number, most people, I run into this all the time. It's really nice when I have a checker that can catch that so I don't run into that at runtime, because not every line of code that I write, I will see at runtime immediately when a customer uses it. If I have unit tests, hopefully I'll catch it. But there's so much code that is not just unit tested that you want that extra layer of security ahead of there. I like both type checking and unit testing to catch things like this. So we talked about runtime. There is no runtime cost for Python type hinting. It is all done at static code analysis. The Python runtime doesn't look at those types whatsoever and won't restrict you any which way. There are libraries that can force that. I'm not going to talk about those in this talk because I don't know anything about them. Not that that's stopped me from giving talks before. But, it's a separate step before you're running your Python code at check time. So if you have CI/CD pipelines, great place to put in here. If you're running talks to run your tests, put mypy in there as well to catch these sort of errors. It catches so much. So the remainder of this talk, I want to talk about how can we use types more effectively in Python. So we talked about composite types. I can use composite types in my type hinting. So I had some color enum, I can type hint on that. I can create a list of presenters if I need to and say, hey, that's how I should be interacting with this. I can even use callable. So this is if I wanted to save a function or a lambda, something that has a call method on it. This is, matcher is a function that takes an int and returns a bool. So if you're doing some more functional programming, you can use callable as your type hinting as well. Functions are types. There's also generics. So you can look at generics on here. T is a type var, and its name is T. And this lets me genericize certain ideas. Like, hey, if I have a function called first, it takes a sequence of some type T, and it returns an element of T. So if I have a sequence of ints, it should return an int. I don't want to use, there's something called an any, which is kind of your catch-all type. I don't want to use that because I don't want a sequence of ints to return a bool or a float or a string. I want a sequence of ints to return an int. I can create relations between types by using these generic ideas. Now there's a problem here. What happens if sequence is null? What happens if sequence is empty? Runtime errors, and this is alluded to as the billion-dollar problem. Someone, I forget who it was. Does anybody know who coined the billion-dollar problem? I wanted to say it was C.A. Hoare, but they pretty much said, hey, if you do have null pointers in your language, I feel like that one design choice has cost billions across the industry over time because there's nothing in the type system, the timing said that, where I can catch nulls or nuns or like empty lists or anything like that. Because if I have say something's an int, I can assign it to none, and now I have to do an is none check every time I want to go use that int. And I have nothing to tell me, hey, you missed one. And that's a problem. So instead of writing the sequence here, we can actually say, well, let's throw an exception then, because that way at least we'll handle it gracefully. And this was like kind of the way of thinking throughout the 90s, I feel, of like, yes, we're going to throw an exception every time something went wrong. And a lot of people who like really strong type systems said, whoa, 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 exceptions cannot be represented in a type system. That's still a runtime error that is really easy to mess up. So we actually have types that can help us out here. And so what I have is a union over here. A union says this type can be one or the other thing. It can be a T, which is the first thing of a sequence, or it could be none. Now, whenever I try to use this, my type checker will say, hey, are you checking to make sure it's not none before you use this? If you're familiar with, like a Haskell maybe monad, or if you're familiar with optionals and a lot of other languages, same idea. So I can say, hey, if my sequence is empty or if it's null or whatever, just return none. Otherwise, return the first element of that sequence. That's useful. There's actually a shorthand for this. You can just say optional of T. It's the same thing as a union of type and none. So you have optionals in Python. And that's nice because if I said something along the lines of, hey, I have a collection, it's a list of ints, I make a list, I call the first function on it, and if this function expects an int, it will create an error saying, hey, I can't take an optional of int. I can only take an int. If you do an if not none check, like if f is not none before this, type checker is happy. So the type checker is forcing you to check for none or and any of your sort of types, which is critical. How many people have ever run into like a none, like trying to access an attribute on none in Python? Fair amount of hands. I run into it all the time. It's like, oh, why is that none? If I can express it in the type system, it might catch it earlier. So what if I want to restrict values? So int is wide open. How do I restrict it? Well, we have something called literals. So in this code, I have x is an int, y is a string. These are literals right here. The one, the ABC. They're what's being assigned to the variable, but they're kind of like naked out there in your code. Anytime you see just like a raw number or a raw string, that's a literal. And we can actually express these in the type system. You might say, why would I ever want like a type to be just a certain literal? And well, we use it all the time when we open. I've never seen like that R at the end or that W at the end, whatever your opening mode is. I've never seen that saved off as a variable and like passed in, or like used as a string and passed in elsewhere. Maybe some of you have. I have never. That R would be great to say, hey, I am only expecting the literal R or W, any of that sort of stuff. So I could say, hey, open path takes a string. My mode is a literal where I take R plus, W plus, and there's like 18 more things that this can actually take. I don't want to get into all of them. But the point is I can restrict. So if someone says, oh, I'm going to pass in Pat Viafor as the mode, the type checker can catch that. And that's super useful. And literals can be composed, which is really nice. So if I had a read-only mode, a write mode, I can actually just compose those in all modes. So you can have a literal of a literal of a literal, and it all flattens out and plays nicely. It's really nice that it does that. Really useful. So if you ever have an API that takes a specific range of a few numbers, maybe, or some string literals, consider literals. What if I want to restrict subtypes? So I showed this presenter class before. What a subtype is something that can act as a substitution to this presenter. So let's say I have a keynote presenter. It's the same, it inherits from presenter. You'll see that up at the top, keynote, parens, presenter. It says, hey, I inherit all the same behavior the presenter has. However, I'm going to add on a little bit more behavior. When I give a talk, not only will I increment the talk counter, but I'm also going to create a talk counter as a K, so I can track how many talks I've given as a keynote. Then we can do other things to say, how do I get keynotes? But that doesn't really fit on a slide. I've enhanced this type. The keynote is a presenter and then some. I never want to conflict with that base type. If you've seen my solid talks, I've talked about Liskov substitution principle. That gets you into all sorts of problems as soon as you start conflicting with your base type. But what if I want to restrict subtyping? What if, I really don't want my keynote to be subtyped any further? You might have valid design reasons to do this. There's now a final in Python. Python's finally caught up to like mid-90s Java. Final says, hey, this function can't be overridden. So if I wanted to create some other, somebody who inherits from Keynote, I cannot override givetalk. Well, I'll take it back. In runtime you can. In the type checker you cannot. Whenever I say you can't do something, what I'm really saying is the type checker, mypy or whatever type checker you're using, will catch that as an error. Again, there's no runtime cost to any of these. It's still valid for, and like Python, for me to go override this, and it won't even run with a runtime. It won't even fail with a runtime error. But if you're trying to convey some information to future developers and trying to restrict them, consider final. You even put final on the class, so you say nothing can be overridden in here, and I don't want you to be subclassed. So it's just a really useful way to say how to restrict your subtypes. But wait, there's more, says our good friend Billy Mays. Final can also be used to create constants. So I like this value of final more. I don't like restricting subtyping a whole lot. Making things constant sounds like a lot better, because right now we have to kind of do shouty uppercase to say this is a constant, and then maybe Pylint complains about it. But here you can have the type checker check it, and again, it's conveying information to future developers. You don't have to rely on someone's adherence to PEP 8 for shouty case to see. Shouty case is all uppercase for those who can't perceive like Pat lingo. If this is much more informative to developers of, hey, this is final, please don't change this. All right, how do we get more specific about types? So this is a type of a dict. It says I'm mapping a string to an int. So I have string keys, integer values, and I'm creating a type called mydict. This dictionary will type check just fine. It is a mapping from string to int. This one won't. I have an extra key that's string to string. That's annoying. How many people work with dictionaries exclusively that always have a mapping from one type to another type and never mix types in their values whatsoever? Not many. I certainly don't. I have like ints and strings. I might have a list in there. That won't type check. I might have a nested dictionary in there. Anyone who's ever done any JSON is like, wow, yeah, I nest dictionaries like 12 deep. It's fine. This is fine. I can't type check that really easily unless I start doing like weird, like, oh, this is a string to an any. But that's a wide open door. I can put anything in there now, and it doesn't really convey anything for types. So Python 3.8 says, oh, you know what? I'm going to give you typed dict. Python 3.8 came out like a month ago, so this is still a pretty new feature. I really like it. A lot of people complained about Python 3.8, like we got the walrus operator, and people were like, whatever. But there's actually a lot of cool typing stuff in 3.8. I don't remember if literals and finals were introduced in 3.8. I want to say literals were. Someone can check me on that. But typedict certainly was. Typedict says I can create a class, so my dict, and say, hey, I have to have an I that's an int and a name that is a string. And then I can also inherit from typedict, so I have a new dict that inherits from my dict. That total equals false pretty much says all these fields are optional. So I can have required fields in my dictionary, and I can have optional fields in my dictionary. That's really nice from a type checking standpoint. So I and name would be required. My list and nested would be optional. So I can then say, hey, I can say, here's my new dict. This type checks. Even though I've mixed and matched things, I have a list as a value here. I and name required. My list was optional. I had another nested thing that was optional. It doesn't matter that it's not here. That's great, because we always have like some dictionaries.
What was total?
Total says that these fields are not required. So my list and nested aren't required. Do you require totality in this dictionary? It's by default true. So when I say my dict, I and name, total is true. I expect the totality of that dictionary to be there whenever I use this type.
I've been using something called typing. How is that different from data classes?
Typing?
Yeah.
Typing is the module, so you can do. So typing is where like all these typedict and things like that happen. Data class, I don't really want to go back 60 slides.
Yeah.
Catch me at the end. Data classes are how do I like create a.
But have you been talking about typing this whole time?
Yes.
Okay.
Yeah.
Thank you.
Typing is the library where typedict, literal, final. I'm going to talk about protocols later.
All right.
They all come from. Whenever you see things like list, that comes from the typing module from typing import list. Slideware has to be sparse just because I only have limited space on here. I have left off all my imports. Okay. So at the top of almost all of my code, you can assume from typing import like 12 things.
Right.
So yes, the typing library, the typing module, is where you get most of the things like typedict, list, dict, union, optional, tuple, callable, a whole lot of things like this, any, all those come from the typing module. So required, not required, lets me able to typedict this just fine. And you mentioned data class. I'm going to say this. I like using data classes more than I like using typedicts. If I'm writing my own types, I would prefer to use data classes because I feel like, well, I'm not just wrapping up a dictionary and putting a type on there because I like having some of that interface on there. However, if you have like JSON API, if you're already interfacing with like dictionaries from a legacy API, that's where typedict comes in. You can say, hey, I read in some JSON from the network, I do validation, make sure it's all the right types, and I return a dictionary of type here because I now can have a reasoning, I can make that assumption that this is that type moving forward and type check it from processing power moving forward. That kind of answer your question?
Yeah, I think so.
Yeah, and catch me after if you have more questions too, or just interrupt me if you have questions, it's fine. We got time. All right. The last thing I wanted to talk about is how we get more specific about types. Well, duck typing, the duck's going to show up all throughout this talk. Duck typing had a problem when we started talking about types. If I have this print and clear of C, which is some collection, I print it, I clear it, what type should that be? What type should C be? A collection? There's no type called collection. There's a sequence. What if I wanted to write my own class that had a clear function? That's not a sequence. Duck typing says that's perfectly fine. I mean, I could say like, well, I could do a union of a dict and a list, and then as I keep coming up with all of my own, I have to find my own collection subtype here. I'm not using a built-in type. I could put like, maybe I have a custom class and I just keep adding on to that union every time I think of something. It's kind of ugly. Protocols, also introduced in Python 3.8. It is structural subtyping. It is duck typing at your type check time. What I can say is I can create a class called clearable, and it inherits from a protocol. I say, this is a stub function. I don't really need a whole lot of implementation here. I just say, hey, there's a function called clear that returns none as part of this protocol. And I'm just saying pass, ignore whatever happens here. I could return none. There's not a whole lot of meaning to this implementation. So now when I say print and clear, I can say, hey, I'm expecting a clearable. I just print and I can clear it. Now I can create a custom class that has cleared. I don't have to say anything about the protocol here, but as long as I have a function called clear that returns none, it can slot in to handle and print and clear. So I can pass in a set, a dictionary, a list, custom class, it doesn't matter. As long as I adhere to that protocol, as long as I have the same sort of structure that this protocol is expecting, type checker is happy about it. That's pretty cool. I actually really like this because I've been complaining about this for a while. Like this PEP that was introduced this feature was years in the making. I was really glad when I saw it. Like, oh man, I wanted this to happen. Thank you for making it happen. Finally in 3.8. Protocols can also act as subclasses. You can subclass protocols from protocols. You can subclass non-protocols from protocols. It got a little hairy as I was starting to get through that. That's some more homework for you. If you want to go learn how protocols can be subclassed, go read the PEP that handles protocols. Yeah. So, takeaways of this talk. Why do we have types? Well, I've said we want to communicate intent, and we need tooling. So, when you are writing your code, think about what intent you want to convey to people in the future. Types are a great way of doing that. Should this be mutable or immutable? Should this have some invariant around it? Should it, be ordered a certain way? Typing, should it be final? Should I expect literals? Should it be some sort of dictionary? Should it be some sort of protocol? Convey the intent forward and use tools to help you catch mistakes. Whether it's your IDE with mypy or type checkers, there's a whole lot of tools out there. I've just started talking about mypy. There's other ones. MyPy is almost like the reference implementation. Google has their own type checker, I believe. Not sure if Microsoft does, but take a look at them. Go research them. Remember, what is a type? Types, how data is represented in memory. I don't really care about that for this talk, but more importantly, what operations are possible on it. That's kind of the key of knowing what is my tooling catching is checking when I'm having mismatches of operations and behaviors. What intent do I want to convey to people in the future? What operations are allowed on it? And remember, Python is duck typed. We probably should have named this duck in the beginning because he kept showing up so often. That's kind of the core basis of this whole dynamic typing that Python is. It's not, you have to put your types up front. All the typing things I've shown are completely optional in Python. If you download 3.8 today, you don't have to use a single lick of what I've shown in this talk. However, I encourage you to. My name is Pat Viafor. Thank you very much for this talk. I'm going to handle questions. I went through a lot of stuff. What questions do you guys have?
It kind of bumbles me that you can put all this typing into the program, and then when you run the program, it doesn't care, and it doesn't even error. You can put all this typing in, and it doesn't help you at all at runtime. And I think there's a core, Pat opinion, there's a core philosophy of Python that, yes, that's the way it always has been. And it's kind of interesting. There's been some discussion, like the person who's been pushing Python typing is the creator of the Python, Guido von Rossum. And people were asking, well, why didn't you do this, 20, 25 years ago, whenever Python was around sometime mid-90s, in the beginning? And I don't know an answer to that. Maybe it's just the tooling wasn't there. Maybe it just wasn't the thing. But as we've been building bigger and bigger programs, people are saying, hey, I want typing. One of the interesting things is, let's imagine I have, so what is it? Anyone remember the article that came out recently about JP Morgan's Athena trading platform, how many lines of Python it had? It was in the millions, if not tens of millions. And you can imagine if they just said, oh yeah, well let's upgrade to Python 3 and flip the switch and all of their code breaks because now typing is being broken. Maybe it's, okay, yes it breaks, but we were still handling it some other case. They don't have time to go say, I'm going to go write typing on all of these sort of things. So they're not even going to get to Python 3 by the end of this year when Python 2 dies. They're thinking that's going to be a year or two in the future. I feel like a lot of it's backwards compatibility. I don't want to say, I turn on typing and everybody breaks. And if it was introduced in the language at the beginning, maybe a different story. So what is the code doing at runtime if your types don't match up? Is it
nothing.
Inference?
If it is anything that was a runtime error before typing is still a runtime error. Anything that worked before typing still works. The thing that catches it is type checkers, which should happen before you run your code. When you're building your code,
when you're deploying your code, and, before you put it into a package, before you put it on GitHub, maybe you should be type checking. I have a Git hook in all my Python projects that runs talks and mypy and pilot and all my tests before I do any pushes up to my code repo, just to make sure that I haven't messed up any errors. If you have CI/CD pipelines, do them there. There are tools to catch them. It's just that at runtime it will not catch them because there's a backwards compatibility concern. And there's a cost concern too, not money, but how long does it take? If I had to do checks on every time I assigned to a variable, think of like every operation you do in Python, if I had to do a check implicit in the Python code, if this is of this type, do it this way. And that's not even beginning to talk about dictionaries and protocols and things like that. The runtime will just balloon and how long it takes. And we're already seeing some very long running Python programs. You don't want to increase that exponentially. Other questions? Yes?
Is PyCharm fully compatible with 3.8?
I don't use PyCharm, I do not know. So I use VS Code, and it pretty much just says, hey, tell me where mypy is. Tell me where pilot is. And it doesn't really care about the 3.8 pieces, because I'm still saying, I pointed at my Python 3 interpreter. I expect PyCharm to do something similar, like there's paths set up. Can anyone confirm that? Like, do you set up, hey, here's where my Python is, here's where my mypy is, that sort of thing in PyCharm? Anybody know?
By default, it ships to its own checker, so you can point it to a different checker, but the default checker, I don't know what it's 3.7 compatible. I know that.
Yeah,
But
and
you don't-
yeah, with 3.8 just,
So it is supported 3.8, but they have an initial release to support 3.8, so that may not be the final release.
yeah. So, just for recording sakes, it does have an initial release for 3.8. We don't know what support 3.8 actually has.
It was through PyCharm that I even heard of typing the module, so I'm already with you on a lot of this. Just because PyCharm was like, hey, you should maybe make sure that this, it was basically type hinting before I even put in type hinting.
And they're starting to add a lot of type hinting into like the core libraries and things like that to help catch these sort of things. Like, if I'm calling an, like the abs function on something, I don't want to be passing strings to it. I'm not actually sure that's type hinted, but like they want to start adding more into that. So it wouldn't surprise me if some of the built-in libraries are starting to catch those sort of things too.
One of the reasons for going with a dynamically typed language is to allow you a certain amount of flexibility, because I do C# every day, so I'm all about some types, but once you decide on a type name and once you decide on a type structure, if you want to go changing something, that's going to have a ripple effect throughout your code. So there is a certain, that's what I'm looking for, constraint, I guess, that types impose on you with regard to flexibility. So have you given any thought as to, say, when in the course of an application the development of an application, you might want to start introducing type hinting from the very beginning, or do you wait a little while?
So that's a great question. I personally, if I'm writing a library for other people to consume, I would do type hinting from the beginning. And if I'm not thinking about my types first, I'm not thinking about my UX first. I'm not thinking about how people consume it first. And that's a mistake in my opinion. If I'm writing just one-off scripts that are going to be 100 lines or less, I don't put a single type in there. If I'm at like the top level application code, I'll be a little bit more lenient with typing. Like I might not type my private methods or things like that. But the more reuse I see something having, and the more often I have to come back and touch that code, I'll put typing in it. Because on one hand, if I change typing, yes, there's a big cost to all of that too. On the other hand, sometimes I don't, if someone changes something elsewhere in the code, the typing can catch that. So it's a double-edged sword. It will catch errors and it will introduce rigidity. You have to decide what's right for your project. I like it very much, building small composable libraries, having those type hinted so that other people can use them and build them as they want and they have a robust UX around it. If I have big old monolithic code, I might not do type hinting at the top application layer.
So you mentioned before that doc strings are really great when it comes to keeping these things sorted out. But you can still sort of do type hinting in the doc string, can't you?
You can put, so in doc strings, and there might be two, I have two different answers for you.
Okay.
In the doc string, you can absolutely say, my first parameter is an int. I don't know of many tools that will go introspect your doc string and make sure that's all right. Now there are ways of doing all of this typing in like Python 2 using comments, but so it depends on, do you mean like the doc strings that you put as like a function?
doc string for a function.
Yeah, okay, so like triple quotes, some text,
Yeah.
triple quotes.
Mhm.
Yeah, so does anyone know of any tools that actually introspect doc strings to check types? I don't think mypy looks at that.
I think, well,
Maybe?
PyCharm at least will automatically create doc strings for functions.
That's because PyCharm's awesome.
Yeah.
PyCharm does so much for you.